Hi, in this video we're going to be talking about extreme values of functions, the max and min values of surfaces, so functions of two variables. 3D surfaces have two inputs. So as always, or as is our routine, let's start with talking about what this looked like in Calc 1. In Calc 1, or in one variable, so again, that's a one variable input, the relative max was a peak on a curve. I'm going to phrase this in terms of maxes, but I think you will remember how it works for relative mins. So it was a place where we were locally higher, our y coordinate was locally higher than all the others. There can be more than one. It's not like an absolute max. That's what we'll talk about in the next video. There can be more than one. Both relative maxes and mins are found at critical points. And we're going to stick with the points language now, especially. We might call them critical numbers or critical values because there's only one value that produces them. But now that we'll have two inputs for the rest of the lesson, we're going to stick to the nomenclature of points. Critical points, these are spots where f prime of x equals 0 or f prime of x was undefined. The only issue was that critical points can be inflection points, points where there was no relative maximum, it just looked like there could be, where the function leveled off but then kept increasing in some way, shape, or form. So critical points were the places you need to check, but there's a reason you need to check them because not all critical points will be relative maxes and mins. How does this change in two variables? So a relative max, again, or min, is a peak on a surface. I'll draw a picture on the next slide if those pictures are doing anything for you. So it's a peak on a surface, right? We can still have more than one. Can be more than one. I mean, we can also have less than one. There are functions that have no relative maxes in both one variable and two variables. So there can be more than one, there can be less than one. We're going to find them at critical points. And now that's going to be where both the x derivative, the x partial derivative of f, and the y partial derivative of f are 0. Now, why do we need both of those things to be 0? Okay, at the same point, sorry, at the same x, y coordinate. Why do we need both? Well, if we have f sub x equals f sub y equals 0, then we would have our vector that that's made up of them equals 0, equals a 0 vector. Or we'd have, what's another word for that vector? It's the gradient of f equal to 0. And if the gradient of f equals 0, then the directional derivative along any direction would have to be 0, right? That's how we will make sure that all of the possible derivatives are 0. So it's really the same kind of check. But we have a bigger problem. Now critical numbers or critical points can be saddle points or undefined. Places where we're not really sure what to do with the information. Okay? So, what does this look like? And how can we find them? How can we determine whether something's a critical point or not? Or sorry, how can we determine whether a critical point ends up being a relative max and a relative min? In general, it's still going to be very similar to what you were doing in one variable, in Calc AB, in Calc 1. If I draw a paraboloid that has a relative max to it, what we would see is if I kept f sub y equal to 0, that would mean I'm not allowed to change along the y-axis. That's going along a plane that's parallel to the xz plane. I'd have a parabola. Literally a parabola like in 2D, like in a 2D situation. It's a plane curve. Now, for every single one of those points, f sub y is 0. There's no change in the height along the y direction. If I move slightly in the y direction at any of those points, my z height will stay the same. But you could also notice that so those are all f sub y's, I'm sorry, all equal 0. All have a slope of 0, a change in the z value of 0. But we can see that the x values do not stay the same. The x tangent lines are switching. Now it's a little confusing because we have to adjust for where we're going. These would have f sub x. They would be positive sloped tangent lines, switching toward negative sloped tangent lines. And I know that might not look correct, but it's about the orientation, that the negative x-axis is into the board or into the screen. And so we have to go from into the screen out of the screen. Like if I drew this in the xz plane, it would be this parabola, right? And we're talking about positive sloped and then negative sloped. That's what I'm trying to draw. It's just hard because when we're looking at a paraboloid, it's usually the x-axis is coming toward us. That's what I'm trying to say. So we're very much in a situation where we're still looking for this change from increasing to decreasing. But again, that was me getting lucky, so to speak, or just holding the y value constant, finding a spot on that curve where the y was not changing the z height. So we're going to need a relative max occurs where both f sub x and f sub y change from positive to negative. Just in case you're confused about why we're saying that, if I try to tell that same story by holding the x constant, I would get a different parabola going down the sides, and then we would see the same exact change from the y derivatives going from positive to negative. And if we have a relative min, it's just like AB right now, it's just like Calc 1, occurs where both f sub x and f sub y change from negative to positive. What's the third option? So the saddle points occur when or where one of these partial derivatives change from positive to negative and the other from negative to positive. In case you forget what a saddle point looks like, or maybe I haven't drawn it in a while, it's sort of I keep calling it the Pringle type shape, where in one direction we're going up and then down, in the other direction we're going down and then up. So that would be a saddle point. Okay, that's a iffy drawing to be sure. The hyperbolic paraboloid, and again, we're not that creative, it's called that because it looks like a saddle, right? That's what a saddle point is. I'm not going to draw relative min, it looks like a valley, right? A valley in that surface. So we're still concerned about how to check all of this, but they're all going to occur at critical numbers, critical points. We're going to recreate the second derivative test. So in AB, in Calc 1, the second derivative test was probably not what you used to do. In AB and Calc 1, you probably did more of checking, oh, does the function change from increasing to decreasing, by checking if the derivative changes from positive to negative. The second derivative test was about checking the concavity, because we would say something like this parabola has a negative concavity or concave down. It's concave down behavior. And that was an easy way to check. If we're concave down and we have a slope of 0, then we have a relative max. It turns out that that's going to be an easier thing to check in 3D. So we'll have what we'll call the second derivative test, but it's going to be a little bit more iffy. So we have the second derivative test. We're going to define this function d of a point of any input will equal f sub x. So the second partial derivative with respect to x evaluated at that point times the second partial derivative with respect to y twice at that point minus the second partial derivative with respect to x and then y at that point squared. Okay, so the reason this part's squared is it's sort of using Clairaut's theorem that fxy should be equal to fyx if everything is continuous. If you have trouble remembering this formula, it's sometimes easier to use, it's called the Hessian matrix. You don't have to know that terminology right now, but this this operation is the determinant of a matrix that goes fxx, fxy, fyx, fyy. And again, we would get that same thing if we did this determinant of this matrix because of Clairaut's theorem. I definitely remember it this way, but I don't know. Maybe it's just weird to have to remember it that way. It's just we're going to use all of the second derivatives and mix them in a weird way. To go over what's happening here, this is kind of making sure we have concavity in the x direction and concavity in the y direction, and that they match in some way. If they both are have the same sign, this part's going to work out to be positive. If they both have the same kind of concavity, this part's going to work out to be positive. And that's very helpful to us because of how this test works out. So there's 3 parts to the test. 1, if the value of this matrix, the Hessian, is greater than 0, and the second derivative with respect to x, you could check y, happen to be positive, then we have a relative min. This is the situation where you're thinking of where we have kind of a good measurement of the concavity. The concavity is positive. If the second derivative is positive, we have a relative min. Now, what I just said is not necessarily true. This part had to be positive, and then the concavity in the x direction is also up, basically. More on that in a second. 2. All right, so if this thing, this Hessian, is positive, but the concavity in the x direction is negative, now we have the point would be a relative max. So these 2 cases ignored, well, what happens if that first thing, if that Hessian matrix is itself negative? So maybe these had opposite signs, and then we're subtracting something that's always a square. We're subtracting something that's always a square, so it's always positive. So if these 2 had opposite concavity, more or less, if we had opposite concavity in the x and the y direction, we don't have to check either one of them individually. We would just know that x, y is a saddle point. Four, if this Hessian matrix was equal to 0, or the determinant of it was 0, this would be inconclusive, which is unfortunate, but in a class like this, we're not really going to deal with that too much. We're more interested in seeing if you understand how this test works out. So one more time, we're checking if this Hessian determinant is positive, if this function ends up being positive. Why? Because it means that these 2 had the same sign. And if they have the same sign, and they're both concave up, then we have a relative min. If they have the same sign and we're both concave down, then we have a relative max. If they have opposite signs, this thing is guaranteed to be negative. And we have a saddle point. So how could this happen? Well, it happens that they have the same sign, but this thing, this measurement, cancels it out, so to speak. It's inconclusive because it means we have a very strange function. We have a function that does not really have a relative maximum. This function is somewhat a measurement of how much does this thing look like a problematic function. So once you have all of this memorized, for the first time when you're doing these problems, you're going to want to have that near you. But the steps. So in general, our steps for doing this. We're going to solve the system where f sub x equals 0 and f sub y equals 0 simultaneously. Again, this is the same as the gradient of f equals the 0 vector. 2, that's going to give us the critical points. So find the critical points. Sometimes students will struggle with that step because they'll misinterpret how to solve that system. If you solve that system, it should not be that difficult to find the critical points. 3, you're going to find this Hessian determinant, right? The second derivative test at each critical point. And then you know which of these critical points are maxes, which are mins, and which are saddles. So let's see how this works in action finally. If I have f of xy equals 2x squared plus y squared minus 2xy minus 8x minus 2y plus 2. So I know that looks quite long. It's not that bad. Our first step would be to look at f sub x and f sub y, and we're going to set them both equal to 0. So right now you should pause the video and find them, because this should be relatively easy for you by now. 3, 2, 1. So I'm getting 4x minus 2y minus 8. And again, we're going to set that equal to 0. And then I'm getting 2y minus 2x minus 2, also set equal to 0. What do I mean by solve this system? If I try to solve this system, I would get 4x minus 2y equals 8, and 2y minus 2x equals 2. However you want to use the system, it's pretty easy to solve with elimination here, to be honest. If you add these two equations together, you should get that 2x equals 10, which means that x equals 5. And if x equals 5, then y equals 6. So that means the critical point is only 5, 6. I'm going to put a flag here for you to remember that if there was not necessarily only one y value for that x value, you might have multiple critical points where x was 5. The same thing with y. You could have multiple critical points where the y was 6. But for this kind of a system, there's only one way for the x's and for the x derivative and the y derivative to both be 0. And that's at this point. 2, or that was 2. 3. All right. So now I need to find fxx, fxy, and fyy. In no particular order. You should do that. 3, 2, 1. In this case, fxx is just a constant. fxy, regardless of how you do it, should be -2. What do I mean by regardless of how you do it? If you do the x derivative and then you take the y derivative of this, -2. If you did the y derivative first and then took the x derivative, you should have gotten -2. And fyy is +2. So putting that all together, this function, this Hessian function, is constant, is 8 minus -2 squared, or 4. What does that mean? That means any critical point you find is a relative max or relative min. Like it's always that. So if I plug in the point 5, 6, there's no x's or y's to replace, so that's 4, 2. And that's positive. What about fxx at this point? Well, that was also already positive. It's always 4. So therefore, 5, 6 is a relative. If they're both positive, it means we have a generally upward concavity kind of situation. So we're at a relative min. And you could find the z coordinate of that function just by plugging it into f. You would get negative 24. But, you know, that's not really the point of the problem. The point of the problem is to see if you can follow through all those steps and get to the final answer. So those are the basics. In the next video, I'm going to try to go over some more of the tricky kinds of systems you can get into. Thanks for watching. See you in the next video. Bye.